Calculating limits of sequences. So we have several tricks, properties for calculating limits of sequences. So this is called theorem 1. Let a sub n and b sub n be sequences of real numbers, and let a and b be real numbers. The following rules hold if the limit as n approaches infinity of a sub n is equal to a, and the limit as n approaches infinity of b sub n is equal to b. So first you have the sum rule. And by the way, you had corresponding rules for limits in Calc 1. All of these rules have a Calc 1 version for regular limits. The limit as n approaches infinity of a sub n plus b sub n is equal to a plus b. Same for subtraction, skipping down to numbers 4 and 5. Same for multiplication, same for division, as long as b does not equal 0. And then in number 3, you have the constant multiple rule. The limit as n approaches infinity of k times b sub n is equal to k times b for any number k. All right, and we will see how some of those are used in examples coming up. All right, remember the sandwich theorem? We've actually used the sandwich theorem in this course, I'm pretty sure. This is theorem 2, the sandwich theorem for sequences. Let a sub n, b sub n, and c sub n be sequences of real numbers. If a sub n is less than or equal b sub n is less than or equal c sub n, for all n beyond some index big N, and if the sequences a sub n and c sub n both converge to L, then the sequence b sub n also converges to L. And the picture really helps you understand why that's true. So you have the, and by the way, I think some calc instructors call this the Goldilocks theorem. Here you have a sub n, which is too cold. You have c sub n, which is too hot. And you have b sub n, which is just right. And if the cold sequence and the hot sequence are both approaching L, then the just right sequence, which is trapped in between, also has to approach L. Okay, and I will definitely use that in one of my examples. All right, I think this is the last theorem that we need to look at before we get into more examples. This is the continuous function theorem for sequences. I have used this, well, at least the Calc 1 version in this course. I don't think I was really explicit in talking about how I was using it. Let a sub n be a sequence of real numbers if a sub n approaches L and f is a function that is continuous at L and defined at all a sub n, then the sequence f of a sub n approaches the number f of L. So when I use this theorem, at least the Calc 1 version and also the Calc 2 version, often I'm using it to push a continuous function inside a limit or pull it out of a limit. I did that a lot in the L'Hopital's rules section, for example, when we got to the later part where we had to introduce a logarithm to get an exponent down. And I would push that logarithm inside the limit. So that's where I was using that. Here we go, examples. So which of the following sequences a sub n converge and which diverge? If the sequence converges, we want to find the limit. So here are the 4 examples. Let me switch over to the tablet. All right, so letter A here, it turns out, is a great excuse to use the sandwich theorem. Notice that the number -1 to the n is always either 1 or -1. So that means that it has to be between -1 and 1. So I think I can get away with saying that n plus -1 to the n over n is always greater than or equal to n minus 1 over n, and is always less than or equal to n plus 1 over n. Okay, so now I just have to show that the bottom sequence and the top sequence converge to the same limit. And you might already be able to see that they can. The limit as n approaches infinity of n minus 1 over n. This is one that I would feel kind of sad if you used L'Hopital's rule on. That is really not necessary because you can just rewrite this as 1 minus 1 over n, right? Just by breaking it up into two fractions. So as n increases without bound, that gets closer and closer to 1 because 1 over n is approaching 0. The limit as n approaches infinity of n plus 1 over n. Well, let's write that as 1 plus 1 over n. That limit is also 1. Okay, so this sequence is approaching 1. This sequence is approaching 1. By the sandwich theorem, the limit as n approaches infinity of n plus -1 to the n over n is equal to 1. So that sequence converges to 1. All right, next example, a sub n is equal to 2 minus 1 over 2 to the n times 3 plus 1 over 2 to the n. All right, the limit as n approaches infinity of 2 minus 1 over 2 to the n times 3 plus 1 over 2 to the n. So I think in this problem, they want us to use the product rule for sequences, which on one of the previous slides was number 4. I probably wouldn't get mad if you didn't actually write this out because it's pretty clear, I think, what happens with this sequence. But this is how the product rule is used. All right, as n goes off towards infinity, 2 to the n absolutely blows up, right? And so 1 over 2 to the n approaches 0. Therefore, the limit as n approaches infinity of 2 minus 1 over 2 to the n is 2. And the limit as n approaches infinity of 3 plus 1 over 2 to the n is 3. And therefore, this sequence a sub n converges to 6. All right, letter C. Rats. Okay. I just realized there's going to be a theorem about this in a little while, but they haven't told it to us yet. So I guess I have to do it the long way. All right. Hopefully you have some recollection of doing something like this at some point. Okay, the limit as n approaches infinity of 1 minus 1 over n to the power n. Well, let's check the form of that. As n goes off towards infinity, 1 over n approaches 0, which means the base of this exponential expression is approaching 1, and the exponent is approaching infinity. So this limit has the form 1 to the infinity, which is an indeterminate form. Okay. So that means I am thinking about using L'Hopital's rule. Now, let me tell you about a little hang up of mine, and this is probably, scratch that. This is definitely something that I would not take points off for. I can't promise that you're Future instructors might not if this comes up. L'Hopital's rule involves taking a derivative at some point. And the only type of function that you can take a derivative of is a continuous valued function, which means the values of the variable can be any real number. Sequences are integer valued functions. They only take on values that are integers. And strictly speaking, you cannot differentiate a function like that. So I always feel the need, all right, think of me as, maybe a little obsessive about this. When I'm getting ready to use L'Hopital's rule, I change my variable to x, and I think of x as a continuous variable. I don't like to take the derivative with respect to n. Doesn't feel right. Okay. And again, it's because it's a discrete variable. Okay, so you remember how we dealt with these in chapter 7? I'm going to call this value L, and then I'm going to take the natural log of both sides. The natural log of L is equal to the natural log of this thing. Oh, goody, I just realized that at some point here, we're going to be using that continuous function theorem. Hang on, I almost forgot that I changed this variable to x. All right, in fact, I'm going to use that right now. So by that continuous function theorem, I can put the natural log inside the limit. The limit as x approaches infinity of natural log 1 minus 1 over x to the power x. And then by my favorite property of logarithms, I wish you could see my dog right now. She's looking startled because I just whistled. All right, the limit as x approaches infinity of x times natural log 1 minus 1 over x. And let's see. I think I have, yeah, I have something set up on the next slide, so I need to, so we can get rid of this. All right, so the last thing I'm going to do with that, and let me remind myself that this is natural log of L, is equal to the limit as x approaches infinity, natural log 1 minus 1 over x over 1 over x. All right. You know what? I don't think I've ever used this trick before. It's not absolutely necessary. It'll just make things a little bit simpler after this. I'm looking at that 1 over x. And by the way, this is in the right form now for L'Hopital's rule, because as x approaches infinity, the numerator approaches natural log of 1, which is 0, and the denominator approaches 0. What I'm a little concerned about is that if I differentiate the top and differentiate the bottom, it's going to get a little messy. So here's a trick that I sometimes do. I don't think I've ever done it here before. I'm going to make a substitution in this limit. I'm going to let u equal 1 over x. Which is going to make this limit natural log 1 minus u over u. And then as x approaches infinity, 1 over x approaches 0, specifically from the right. So if you make this kind of substitution in a limit, you have to talk about what your new variable is doing. Okay. Not absolutely necessary. It's just going to make the derivative simpler. Okay, so now I'll use L'Hopital's rule because, again, it is in the correct form. It's got the form 0 over 0. the derivative of natural log 1 minus u is 1 over 1 minus u times the derivative of 1 minus u, which is -1. And the derivative of u is 1. As u approaches 0 from the right, that thing is approaching -1. All right, and then just don't forget that that is not your answer. That is the natural log of your answer. Natural log of L is equal to -1. So now if I exponentiate both sides, I get that L is e to the -1, also known as 1 over e. So this sequence converges to 1 over e. All right, last example in this batch. A sub n is equal to n minus the square root of n squared minus n. All right, this is a kind of tricky one. Even checking the form is a little tricky. Remember, one of our indeterminate forms is infinity minus infinity. And I guess you could argue that you have an infinity minus infinity going on just right there, right? But the point is that the n squared overpowers the n as n gets larger and larger and larger. So n squared minus n is approaching infinity. This thing has the form infinity minus infinity. Okay, so here's how we're going to put that in a form that we can deal with. So we're looking at the limit as n approaches infinity of n minus the square root of n squared minus n. I am going to multiply the top and the bottom, now that it has a bottom, of that expression by the conjugate of that expression. So by n plus the square root of n squared minus n. All right. Go back to my regular color here. Okay, notice in the numerator we have AU minus V times AU plus V, which multiplies out to U squared minus V squared. So that would be N squared minus the square of the square root of N squared minus N. And then downstairs we just have N plus the square root of N squared minus N. All right, of course, the square and the square root will cancel. So we'll have n squared minus the quantity n squared minus n. Denominator has not changed. And now in the numerator, those n squareds are going to cancel out, right? And by the way, we have to distribute that minus sign. So that's going to change the sign in front of n to positive. So what we're going to have is the limit as n approaches infinity of n over n plus the square root of n squared minus n. Now, I'm not sure what would happen if we used L'Hopital's rule on this. It might be okay. That square root of n squared minus n will be a little messy. So it occurred to me that this limit is technically a Calc 1 problem. It's not the easiest Calc 1 problem. The way that I'm going to evaluate this limit is like this. I'm going to multiply the top and the bottom of this fraction by 1 over n. which is going to give me, well, the numerator will just be 1. And then in the denominator, I will have 1 plus, and let's write square root of n squared minus n over n. Okay, so I have one last trick up my sleeve for that square root expression. I'm going to think of this n as the square root of n squared. And I'm going to push that n squared inside the radical. See what I did there? And now if you break that into two separate fractions, you get 1 over 1 plus the square root of n squared over n squared, which is 1, minus n over n squared, which is 1 over n. And now it's finally in a form where you can just evaluate it as n increases without bound. 1 over n is going to go off towards 0, leaving you with 1 over 1 plus the square root of 1, which is 1/2. So this sequence converges to 1/2.